The other big application of our double integrals, other than center of mass probability distribution, is to talk about surface area. When we consider a function of x and y, we're really considering a surface already. So here we have some surface in 3D above a region in the xy plane. So if this is z equals f of xy, and then I've got some region in the xy plane. Let me make a rectangle just to start with, so my work is a little easier. There's my rectangle, and it goes from A to B in X and C to D in Y. Then I could think of what happens if I look at the surface part over our rectangle. So above that rectangle is some piece of S. And I've drawn it so that it kind of arcs forward towards us, and it arcs down as we go from left to right. I would like to know, what is the area of this piece? Now, here's a link to what we were talking about on Wednesday. That area should be related somehow to the area of R. But when we lift, we distort that area. So I can think of what's happening down here as being bent and shift and twisted as we go up. So how can I get a good picture of this area? I'm going to use an approximation. I'm going to break it up into little polygons, and I'm going to tile that surface just like every 3D game in the entire universe, right? When you see a picture of a building in some game, it's not actually physically there. It's a bunch of polygons in the middle of the screen, right? So it depends on the resolution. So I'm going to make little squares. I'm going to make my little square somewhere in here. So at some point, I'll take a little square from here, and I'll lift that little square up. And now I'm going to ask the same question. What's the area of that little square? But it's a square. All I need to know is the length of each edge. But I can go you one better. If that's a square or a little rectangle or something, I can think of this as if it was a parallelogram. Rectangles and squares are kinds of parallelograms. And now my brain says, wait, I remember this. I remember this. We had a formula for the area of a parallelogram in chapter 12 in vectors. So dig back into chapter 12. Let's see if we can find that formula. And there was another way to get that same area. And the length of u and the length of v, u and v were the vectors that made up the side. Theta was the angle between them. And the area was length of u, length of v, sine of theta, but there was another formula for that. Aha. So let me go back over there to the surface. And let me think about the edges of this piece. This piece right here is up here. And this piece here is here. Those two edges could be made into vectors. If I knew what vectors those were on the surface of S. But wait a minute. I didn't pick this square out of thin air. I didn't pick this little rectangle for shits and giggles. I picked the rectangle that would be the closest approximation to the surface. Linear approximations. Linear approximations come from tangent planes. And tangent planes come from my partial derivatives. Hey, that stupid hat with the damn things on it sticks in your head, doesn't it? Now it sticks to your head. This is actually up here. This is, I can't quite get it to stick to my head, but now it's on top. There you go. It was my society class. Okay. How do I figure out what the vectors are here? The vectors u and v are tangent vectors to the surface at a point. But not only that, we know which direction they go. Which direction is this vector pointing in? That's pointing along the y-axis. And this vector here is pointing along the x-axis because they came from this little square. And they go in the direction of the axes. Which means I need to take a directional derivative. But because I'm taking the directional derivative in the direction of an axis, that's just a regular ordinary partial derivative. Let me name the vectors. We called them u and v up here. So I'm going to go back to the x and y plane. I'm going to think of my little box, and I'm going to call this vector u, and I'm going to call this vector v. So the u vector is going to go along the x-axis. But that means that that vector points in the direction 1, 0. Along the x-axis, that's 1, 0. But up here in my picture in 3D, slide back up, it could be going up or down as well, right? But the slope would be partial of f with respect to x, which means this vector looks like that. What's v? There's just one problem with those two vectors, and it's my fault. I really don't want to go a whole 1 unit. I only want to go the width of this little box, right? So if this box has side lengths that are delta x and delta y, because I'm making a little bit of area, that should be delta A, then I should really multiply this whole thing by delta X. And I should multiply this whole thing by delta Y. So I go this way, but I only go this far. I go this way, I only go this far. And then I can piece together all of these polygons. Now, you're still looking at me like I'm a space alien? Take a look on page 1026. Here's a picture out of the textbook. We have the little square whose width is delta X and delta Y in the XY plane down here. And then we lift it up to our surface and we take the tangent plane and we chop out this little piece. And the sides of those little pieces are the two vectors we just came up with, multiplied by the appropriate lengths, delta X and delta Y. Does that make more sense with their picture than with my crappy picture? Whenever we draw a picture on the computer, we get that checkerboard pattern, right? Those checkerboard squares are these little squares. If we graph in any of our graphing software, the little surface is covered in all these little squares. Those are the squares I'm approximating right here. Instead of letting them curve, I'm just using little flat squares. Questions? He was flashing and going back to his office to get something. Okay. This is the actual edge of the vector. So the area of my little piece is the area of the cross product. Means I need the cross product of these vectors. I'm going to do a cross product. I, J, K, 1, 0, partial with respect to X, 0, 1, partial with respect to Y. Oh, but then I have to multiply by delta X and delta Y. Those numbers were just multiplied by each of the vectors, so I can just multiply by the numbers. Do the cross product. Look like I'm going to the dirty. Two things I want to note about this cross product. What direction does this cross product point? It points up. Partial with respect to x, partial with respect to y. Oh, it points up. This is an upward pointing surface vector. Points out of our, hey, wait a minute. It points out of our tangent plane. This goes the same direction as my gradient vector. Second, I don't actually want the vector. What do I want for the area? So I don't actually want this. I want the length of this vector. How do I get the length of that vector? Oh, right. Square root of all the bits squared. Hey, wait a minute. That means the minus signs go away. But look at what I get. I get the square root of fx squared plus fy squared plus 1. And then delta x squared, delta y squared, but they're under the square root. So that's delta x, delta y on the outside. But isn't that the same as dA? I took off the AB part. You could put them in if you wanted. That's the same as delta A. I'm going to rewrite this to put the 1 at the front. And all of a sudden, I hear in the back of my head, I've seen this crap before. I've seen something looks really, really, really similar to this before. This semester and in Calc 2. What's this look like? What's that? Arc length. That's arc length. This setup looks just like the setup for arc length, but we're going in two directions because it's a surface, not a curve. Son of a... This is arc length in 2D. Arc length told me how much wiggle was in. This tells me how much wiggle is in my surface. It's the same damn idea. But that means this was the area of one little square. Instead of looking at one square, I want to look at all of them. I got to add them all up. And then I got to let the squares get smaller and smaller and smaller. I'm doing a double integral because I got to do it dx and dy. The area of a surface. Is given by the double integral of this square root term. And this looks exactly like the arc length calculation. And because it looks like the arc length calculation, if these aren't rigged, we are up the creek. Because that square root's gonna mess with me hard. Mia, Jack, elliptic integrals look like this. Kovalevskaya. That's the crap she was talking about. And the one we talked about yesterday in history, the abstract, these are the elliptic integrals. That this is the crap they're working on, and they end up with all these new techniques because this stuff sucks. We're only going to do the rigged ones. I promise we're only going to do the rigged ones. Okay. So let's examine this idea for a moment. I'll start with a problem I know works out nicely, I hope. This should be rigged, because if we're not rigged, we're going to be in deep trouble. Find the area of the surface, part of z equals x squared plus y squared, under the plane z equals 9. So let me start with the first question. What shape is that? Almost. If it was x squared plus y squared equals a number, it would be a cylinder, right? Because then the radius would be the same. But this changes, the height changes as we go out. So we're going to go out and go up. Let's do it by traces. If I was just looking at z equals x squared, I'd get a parabola this way, front to back. If I was just looking at z equals y squared, I get a parabola side to side. Oh, this is a parabola and this is a paraboloid. And it opens upward. But we stop at a height of 9. So here is my upward opening paraboloid, but I chop it off at a height of 9, right? So here's a question for you. What's the region in the XY plane that this surface lives above? And not just any circle, the circle where x squared plus y squared equals 9. If I'm going to do a double integral, I need a region in the xy plane. We just determined what that region is. I want to look down at my paraboloid from above. When I look down at my paraboloid from above, I see a circle. Not just any circle. It's where z equals z. It's that circle. Let's set up the double integral we want for the area of the surface. Area equals the double integral over R of something dA. What's the something Goes under that. So let's figure out what those are. Partial with respect to x. Partial of what with respect to x? The function describes our surface. So this is our f of x right here. X squared plus y squared. So my partial with respect to f, with partial of f with respect to x is squared, and then partial with respect to y. dA. Now, here's the problem. Double integral over my region, square root 1 plus 4x squared plus 4y squared dA. This integral sucks. But this is rigged. This is going to work. Polar. Because I'm integrating on a circle. Let's do this sucker in polar. Okay, wait a minute. If I'm going to do polar, then the dA is going to be r dr d theta. What about the square root part? What's the function become? Well, the r is out there. So the 1 plus 4r squared is the only part that stays in the square root. Okay, I need one more thing. I need the description of r in polar coordinates so that I can have the limits for this integral. What are r and theta bounded by to make this disk?
uh, 0 and 9 for our 0.
Almost. Because here, 9 is r squared. It's x squared plus y squared equals r squared. So instead of 9, it's 3. But it is 0 and 2 pi for the angle. Now, if I have dr on the inside, then 0 and 3 go on the inside. If I have d theta on the outside, 0 and 2 pi go on the outside. And now, I can integrate. And if I really want to be sneaky about my integration, I can separate this into two different integrals using my Fubini corollary. And I can say, hey, there's no other theta bits in here except d theta. So this is really 1 times d theta. So I'm going to make it the integral of 1 d theta, and then the integral 1 plus 4r squared under a square root r dr, and just multiply those two together. Whew. This integral is a piece of cake. What about this one? I certainly could do integration by parts. Integration by parts is going to hurt. Because I have a radical piece in there, and when I do the derivative of a radical piece or the integral of a radical piece, that's really going to be messy. As a matter of fact, if I go through and I start thinking about my integration by parts, I do logarithmic, inverse trig, polynomial, exponential, trig. Is radical in that list? Ooh. Seeing that root there, I think I want to stay away from integration by parts. Because this one's actually an easier method. I'm going to just do a u substitution because I have that r on the outside to act as du. No, this is why I said these are rigged. Because if I don't end up with something nice under that integral, I am in deep crap. Because what I would have to do if I saw that without something nice on the outside, I'd have to do something like a trig substitution, like tangent of theta. It works, but it's disgusting. Okay, wait a minute. This one is easy, 0 to 2 pi of d theta. This one is going to become the integral of square root of u du with a 1/8 in front. And I'm going to change the limits. So if I put in 0, I get 1 plus 0. That's a 1 down there. If I put in 3, I get 1 plus 4 times 9. That's 1 plus 36, or 37. And that integral is now power rule, and I can do that one really quickly. Square root of u is u to the 1/2. So when I integrate it, I get 2/3 u to the 3/2. Over here, I get a 2 pi. And then I get 1/8 times 2/3. That's 2 over 24, which is the same as 1 over 12. Then it's 37 to the 3/2 minus 1 to the 3/2. But 1 raised to any power is just 1. I have no idea what 37 to 3/2 is, but I'm perfectly fine leaving it like that. You could also cancel the 2 and the 12 and write pi over 6 in front if you wanted. Or you could shove this into a calculator and give me a decimal. I think it's about 117.3. I have a bunch more crap written down, but I'm rounding. Questions? So notice how this drags all of the things we've done in this chapter together. I need to know, I've got to go all the way back to chapter 7. Substitutions in chapter 5. But I needed to do the stuff from chapter 12 where we figured out what the surfaces were, so I knew what I was looking at. I had to set the surfaces equal to figure out what my domain was. And then I had to recognize, hey, this is a domain that's easier to do in polar, so let's switch to polar. And then I needed to do these integrals. Blah. Questions? This problem is actually asking you to find the area of a problem you did for homework. Chapter 15, section 1, problem 12. Gave you a cylinder and then asked you to look at one rectangle piece under it. And that was the piece from 0 to 4 and 0 to 2. This is exactly that little awning shape that you did in problem number 12. Now I want to find out how big it is. So we drew this picture. Goes from 0 to 4 and 0 to 2. It goes up 3 units, but it doesn't quite come all the way down. And then we have something that looks like that. A part of the circle, but doesn't quite reach the floor. Because the circle has radius 3, and it should actually keep going out, but we chop it off before we get there because we chop it off at y equals 2. In order to do this problem correctly, I need z as a function of x and y. What's the equation z equals here? So that's f of xy. Which means when I go to do this integral, those are the partial derivative pieces I need. I need to take the derivative of that, fx and fy. Partial with respect to x, partial with respect to y. What's partial with respect to x? Gee, that one's easy. There are no x's, it's a 0. Partial with respect to y. That's a chain rule problem. This is ugly stuff to the 1/2. So I get 1/2 ugly stuff to the negative 1/2. And then the chain rule comes along. What goes inside that set of parentheses? But wait, there's more. So the 1/2 and the 2 cancel. This has a negative exponent. It goes on the bottom. It has a 1/2 exponent, so that's a square root. And then the minus y stays on top. I'm really happy to see that square root because what am I going to do with partial with respect to y? To do my area integral. Area equals the double integral over some region square root 1 plus fx squared plus fy squared dA. Well, fx is 0, so fx squared is still 0. 1 plus garbage, 0. Now I square this thing, so I get y squared over 9 minus y squared dA. But what's r? What's the region? The rectangle. 0 to 4 by 0 to 2. And it's a rectangle, so you could do this dx dy or dy dx. It doesn't matter. That's my rectangle. 0 to 4 by 0 to 2. So before I do that, clearly I'm going to need to do some algebra on the inside to make my life easier. Because I hate having 1 plus ugly crap squared. So let's simplify this. 1 plus y squared over 9 minus y squared. Common denominator, 9 minus y squared plus y squared over 9. Wait a minute, what happens on top here? So this integral becomes the integral from 0 to 4, integral from 0 to 2, square root 9 over 9 minus y squared dy dx. Wait a minute. I have a square root of 9. What's square root of 9? So I can just leave that as a 3 and only put the square root on the bottom. Oh, wait a second. Wait a second. All of the function parts are in y, aren't they? What's the only part that goes with the x? And the dx, right? I can leave everything else in y, and I can split this into two integrals again, just like we did with the d theta. I can take the dx and move it over here with the 4, 0 to 4 dx, and I can put the 3 all the way out front because it's a constant. And then I'll have the integral from 0 to 2, 1 over 9 minus y squared under a square root dy. And here is where my brain goes, oh, thank God I wrote stuff down on my formula sheet. Because I remember 1 minus y squared in a square root on the bottom. That's the arc sign. That's the inverse sign. And the 9 means I have to do a substitution. And what I end up with here is 1/3 sine inverse of y over 3. From 0 to 2. Thank God that sucker's on my formula sheet, or I'm in deep shit. Integral of dx is just x from 0 to 4, and there's a 3 out there. Hey, wait, the 3 and the 1/3 cancel each other out, and I get 4 times 1/3 sine inverse of 2/3 minus, oh wait, the 1/3 got canceled. Minus sine inverse of 0. Wait, what's sine inverse of 0? Uh-huh. So the answer is 4 sine inverse of 2/3. Grab yourself a calculator, give me a number, you're done. What'd you get me? Wrong button push. a sine of 2/3. 2/3 points that, that's not right. Sine inverse. Did you do sine inverse or sine? Four sine inverse 2/3. How did I know that was wrong before I even did the calculation, man? More than that, we're doing area, right? Do you know a real object whose area is negative? Me neither. So as soon as I saw a negative number, I went, wow, wait a minute. So that's it. The fact that we're doing the square root of a bunch of stuff squared plus 1, that area has got to be a positive. Again, without algebraic rigging, we are in deep trouble here. Without these being simplified to stuff I can recognize and stuff I've seen before, I won't know what the hell I'm doing. So, read through the couple of examples in this section. I will see you all on Monday. Have a wonderful weekend. I sent an email about canceling office hours this afternoon. I'm off to the conference right after my last class. I will see you all then.